Welcome to Sleepy Science Student, where we explore the universe one gentle revelation at a time. Tonight, we're going on a slow, soothing journey into one of the most extreme frontiers of physics, a place where heat itself reaches its absolute limit, where temperature becomes so intense that the very fabric of spacetime begins to tremble and fray. We're talking about the Planck temperature, the highest heat the universe can possibly know. I hope this video isn't too interesting. Though if it does happen to keep you awake, at least you'll be learning something fascinating about the most extreme conditions nature allows. Not the worst way to spend a sleepless night, really. After all, there's something peaceful about exploring the universe's greatest mysteries from the safety and stillness of your bed. Before we venture into this realm of ultimate heat, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It really helps this gentle little channel grow, and it means the world to me that you're here, taking this quiet journey with me tonight. Your support allows me to keep creating these calm explorations of science's deepest questions. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in London at midnight, or listening from a comfortable chair in Singapore at dawn while watching the world slowly wake up? Perhaps you're somewhere in between, in a time zone where the afternoon light is still streaming through your window. Let me know in the comments. It's always such a joy to see the Sleepy Science student community scattered gently across the globe, each of you finding your own moment of peace and curiosity. Now settle in, get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like gentle waves lapping at a peaceful shore. Feel your shoulders relax. Let your breathing slow down. And as we begin this gentle voyage into the extreme physics of ultimate temperature, remember that this video is for educational and relaxation purposes only. It's not intended as medical advice or a replacement for any professional guidance you might need, though it will probably make your mind feel pleasantly expansive as you drift through cosmic ideas. Ready? Let's begin. Now, let's talk about something you've experienced countless times, something so familiar that you rarely think deeply about it. Let's talk about heat. Heat is all around us, in the warmth of the sun on your skin, in the steam rising from a cup of tea, in the gentle glow of a candle. But what is heat really? And more importantly, where does it come from? And is there a point beyond which it simply cannot go? These are the questions that will guide us gently through tonight's exploration. Heat, in its most fundamental sense, is motion. It's the restless jiggling of atoms and molecules, their energetic dance at scales so small that we cannot see it with our eyes. When something is hot, the particles that make it up are moving faster, vibrating more vigorously, bouncing around with greater enthusiasm. When something is cold, those same particles move more slowly, their dance becoming gentler, their vibrations subsiding into quieter patterns. Temperature is simply a way of measuring this motion, a way of quantifying how fast, on average, the particles in something are moving. Think of it like this. Imagine an orchestra warming up before a concert. At first, the musicians play slowly, their notes measured and calm. This is like a cold object, particles moving gently, temperature low. But as the concert begins, the pace quickens. The musicians play faster, with more energy and intensity. The room itself seems to vibrate with the activity. This is what happens as temperature rises. The particles in an object begin to play their cosmic symphony at ever faster tempos. Now, here's where things get interesting. We might think that heat and cold are two separate things, that one is the presence of something and the other is its absence. But actually, there's no such thing as cold in any absolute sense. There's only the presence of heat energy and varying degrees of its abundance or scarcity. Colder things have less thermal energy. Hotter things have more. And there's a lowest possible temperature, absolute zero, about -273 degrees Celsius, where all atomic motion theoretically stops entirely. Particles freeze in place, locked in perfect stillness. But what about the opposite end? Is there a highest possible temperature? Can heat rise forever with no limit in sight? This is the question that physicists began asking more seriously as they developed deeper understandings of the universe. And remarkably, the answer seems to be no. There appears to be a ceiling, a maximum temperature that nature will not permit anything to exceed. And this temperature has a name that sounds almost magical: the Planck temperature. Let's pause for a moment here. Before we move forward into the more technical territory, let's make sure we're grounded in what temperature really means in the first place. Temperature is a measurement of average kinetic energy, the energy of motion. When you have a thermometer and you take someone's temperature, you're measuring the average speed of the water molecules and other particles in their body. The faster those particles are moving on average, the higher the number on your thermometer will be. It's beautifully simple when you think about it that way. Scientists measure temperature in different scales. Most of the world uses Celsius, where water freezes at 0 degrees and boils at 100 degrees at sea level. Americans tend to use Fahrenheit, an older scale that divides the same range differently. But physicists, when they're doing serious work, use the Kelvin scale. The Kelvin scale starts at absolute zero, the theoretical lowest possible temperature, and counts upward from there. Absolute zero is 0 Kelvin, the point where atomic motion ceases. Water freezes at about 273 Kelvin. Room temperature is around 293 Kelvin. The surface of the Sun is roughly 5,800 Kelvin. Now, as we move forward in this journey, we'll be talking about increasingly extreme temperatures, numbers so large they almost stop feeling real. We'll talk about temperatures in the millions, the billions, the trillions of Kelvin. And eventually, we'll reach the Planck temperature, which hovers around 1.4 times 10 to the 32nd power Kelvin. That's a number with about 32 zeros after the 1. It's almost incomprehensibly vast. But don't worry if these numbers make your head spin slightly. That's part of the wonder, isn't it? The universe contains scales so extreme that our minds can barely grasp them, yet we can still understand the principles behind them. The fascinating thing about temperature is that it's not just a number on a thermometer. It's deeply connected to energy, to motion, to chaos, and to the very structure of matter itself. Every substance has a melting point, a temperature at which it shifts from solid to liquid. Every substance has a boiling point, a temperature at which it becomes gas. But these transitions aren't mysterious. They're simply temperatures where the thermal energy becomes sufficient to disrupt the bonds holding atoms and molecules in their ordered arrangements. When you heat ice, you give its water molecules enough energy to break free from their crystalline lattice and flow as liquid. When you heat water, you give it enough energy to escape into the air as vapor. But here's a question worth considering. What happens if you keep raising the temperature higher and higher? What if you heat water to 5,000 Kelvin, to 50,000 Kelvin, to 1,000,000 Kelvin? At some point, the water molecules break apart entirely. The atoms separate. Then, at even higher temperatures, the electrons are stripped away from the atoms, creating a state of matter called plasma, a roiling sea of free electrons and bare atomic nuclei. And if you keep going? Well, that's where things start to get really peculiar. You might think that you could just keep heating something forever, that there's no fundamental limit to how hot something can get. But actually, there are several reasons why this isn't true. First, there's a practical limit. As you add more and more energy to an object, you have to put that energy somewhere, and eventually you run into the fact that the object might collapse under its own weight. If you heat something enough, gravity might pull it inward, compressing it into a black hole. And black holes, as it turns out, have their own intimate relationship with temperature and heat. But we're getting ahead of ourselves. The real, fundamental limit comes from somewhere else entirely, from the marriage of quantum mechanics and gravity, from the place where the rules of the very small collide with the rules of the very large. And to understand that limit, we need to understand a bit about what happens at the absolute extreme scales of reality. We need to understand something called the Planck scale, the Planck length, and eventually, the Planck temperature. And to get there, we need to take a few more gentle steps into increasingly exotic territory. Let's take a breath here. We've established that heat is motion, that temperature measures this motion, and that there might be limits to how hot things can get. These are the foundations. Everything we explore from this point forward will build on these gentle understandings. In the next section, we'll zoom outward slightly and start thinking about temperature on cosmic scales, the temperature of the universe itself, how it changes over time, and what clues scientists have found about the extreme heat of the early universe. Now, we move gently into a question that might seem strange at first. What is the temperature of the universe? If you think about it, the universe is vast and varied. Some places are incredibly hot. The cores of stars burn at millions of degrees. Other places are bitterly cold. The depths of space between galaxies hover just a few degrees above absolute zero. So how can we talk about a single temperature for the entire universe? The answer involves something rather beautiful and unexpected. You see, the universe itself is not empty. It's filled with light, ancient light that has been traveling through space since the earliest moments of cosmic history. This light carries information about what the universe was like when it was very young and very hot. And because of this light, we can actually take the temperature of the universe. We can measure how hot it is, on average, if we were to account for all the light and energy scattered throughout space. This ancient light is called the cosmic microwave background, or CMB. It's often described as the afterglow of the Big Bang, the faint remaining heat from the universe's birth. When the universe was first created, roughly 13.8 billion years ago, it was impossibly hot. Everything was squeezed together in an unimaginably dense, incredibly hot state. But as the universe expanded, it cooled down. The expansion itself stretched out the light, making it less energetic, less hot. And today, that ancient light still surrounds us, though its temperature has dropped significantly. Think of it like this. Imagine you have a pot of boiling water. You seal it tightly and set it aside. Over time, the pot cools down. The heat radiates away into the surrounding air. Now imagine doing this on a cosmic scale. The entire universe is like that sealed pot, and it's been cooling for 13.8 billion years. The light from that original heat is still here, still traveling through space, but it's much cooler now than it was at the beginning. We can detect this ancient light with special instruments, and when we measure it, we find that the universe's current temperature is about 2.7 Kelvin, just barely above absolute zero. Now, 2.7 Kelvin might sound cold, and by our everyday standards, it absolutely is. That's colder than the coldest place on Earth, colder than the vacuum of space near interstellar dust clouds. But here's what's remarkable. If we look backward in time, if we trace the universe back toward its earliest moments, we find that it was dramatically, unimaginably hotter. The closer we look to the moment of the Big Bang, the hotter the universe becomes. And scientists have actually developed ways to estimate what the temperature was at various stages of cosmic history. In the first microseconds after the Big Bang, temperatures were in the trillions of Kelvin. In the first nanosecond, temperatures were in the billions of Kelvin. And if we extrapolate even further backward, toward the true moment of creation itself, toward what physicists call the singularity, the temperature approaches infinity. Or does it? Well, that's where things get complicated, because our current theories of physics break down at those extreme scales. We're not sure what temperature really means at the very beginning, because we're not sure what physics itself means at those scales. Let's pause for a moment and think about what this means. The universe began incredibly hot and has been cooling down ever since. This is one of the most profound discoveries of modern cosmology. It wasn't always obvious. For centuries, People thought the universe was eternal and unchanging. But observations made in the 20th century, particularly the discovery of the cosmic microwave background in 1965, revealed that the universe has a history. It had a beginning. It was born in heat and light and has been gradually cooling for billions of years. This process of cosmic cooling has profound implications. As the universe cooled from its initial blazing state, different things became possible at different temperatures. In the first fractions of a second, the universe was so hot that matter as we know it couldn't exist. Particles would form and immediately be blasted apart by energetic collisions. But as temperature dropped, quarks could bind together to form protons and neutrons. As it cooled further, electrons and nuclei could combine to form atoms. As it continued cooling, atoms could clump together to form the first galaxies and stars. Each temperature regime brought with it new physics, new possibilities, new structures. The universe was like a master chef slowly turning down the heat on an enormous cosmic stove, allowing increasingly complex recipes to unfold. First, you have the simple ingredients, energy and fundamental particles. Turn down the heat a bit, and they begin to combine. Turn it down more, and they form more complex structures. Keep cooling, and galaxies emerge. More cooling, and planets form. Even more cooling, and eventually life becomes possible. Now, scientists study the early universe by looking at the cosmic microwave background and by conducting experiments with particle accelerators like the Large Hadron Collider in Switzerland. These experiments recreate, in tiny spaces, the conditions that existed in the early universe. They smash particles together at nearly the speed of light, creating brief moments of extreme temperature where particles behave as they did in the early universe. From these experiments, we've learned quite a bit about what the universe was like at various temperatures going back in time. But here's the thing. There's a limit to how far back we can reliably study. We can trace the universe's temperature back to about a trillionth of a second after the Big Bang. At that point, the temperature was roughly a quadrillion Kelvin. But beyond that point, our theories become unreliable. We reach a barrier. The barrier is called the Planck scale, and it represents the boundary between the physics we understand relatively well and the physics that remains mysterious and unknown. At temperatures above the Planck temperature, physicists believe that our current understanding of physics, both quantum mechanics and general relativity, breaks down. These two great theories of 20th century physics describe the universe beautifully across a wide range of scales, but they appear to be fundamentally incompatible with each other. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes the behavior of atoms and subatomic particles. At normal temperatures and normal sizes, this incompatibility doesn't matter. But at extreme scales, incredibly high temperatures, and incredibly small distances, the incompatibility becomes unavoidable. And the Planck temperature is the temperature at which this incompatibility becomes critical. It's the temperature at which quantum effects of gravity become so strong that they can't be ignored. It's the temperature at which space and time themselves might break down or become fuzzy and uncertain. It's the frontier beyond which we need a new theory, a theory that successfully merges quantum mechanics and gravity into a unified framework. You might think that temperatures like the Planck temperature have never actually existed in the universe. Surely, once the universe started cooling after the Big Bang, it would never get hot enough again to reach these extreme values. But actually, that's not quite right. Black holes, those mysterious objects that result from the collapse of massive stars, can have temperatures associated with them. And under certain conditions, black holes can actually be hotter than the Planck temperature, at least briefly. Or so some theories suggest. The relationship between black holes and temperature is subtle and fascinating, and we'll explore it more gently in a section coming soon. For now, let's simply absorb the idea that the universe has been cooling since its birth, that it has a temperature history that we can study and trace backward, and that there appear to be fundamental limits to how hot things can get. These limits aren't arbitrary. They emerge from the deep structure of physics itself, from the way nature has woven together quantum mechanics and gravity and the fundamental forces of the universe. And understanding these limits will help us understand not just heat and temperature, but the very nature of reality at its most extreme. As we've journeyed through the temperature of the universe from its current state at 2.7 Kelvin back toward the extreme heats of the early cosmos, we've begun to see that temperature is not just a simple measure of how fast particles are moving. It's a window into cosmic history. It's a thread that connects the smallest scales of the universe to the largest. And it's intimately linked to time itself. Hotter periods in the universe correspond to earlier moments in cosmic history. This connection between temperature, time, and the structure of the universe will guide us as we move deeper into our exploration. In the next section, we'll begin to ask more technical questions about what temperature really is at the quantum level, and we'll introduce some of the brilliant minds who have thought deeply about these mysteries. Now we venture into territory that requires us to shift our thinking just slightly. We're going to talk about how temperature appears when we examine the world at quantum scales, at the scale of atoms and subatomic particles. And this is where things begin to get wonderfully strange, because the quantum world doesn't quite follow the rules we're used to from our everyday experience. In the early 20th century, physicists made a startling discovery. The universe at small scales doesn't behave like the universe at large scales. A planet orbits the sun in a predictable way, following clear trajectories we can calculate with precision. But an electron orbiting an atom, it doesn't quite work that way. It's more like the electron exists in a fuzzy cloud of probability around the nucleus, appearing here and there with certain likelihoods, but never in a definite location until we actually observe it. This is the strange, beautiful world of quantum mechanics. One of the pioneers of quantum mechanics was a brilliant physicist named Max Planck. Yes, the same Max Planck after whom the Planck temperature is named. In 1900, Planck was studying something called blackbody radiation, the light emitted by hot objects. He discovered something puzzling. According to the classical physics of his time, hot objects should emit an infinite amount of energy at ultraviolet wavelengths. But in reality, they don't. There's a peak, a frequency at which they emit the most light, and beyond that peak, the emission falls off. Planck realized that light doesn't come in continuous amounts. It comes in discrete packets, little bundles of energy he called quanta. Each quantum of light, each photon, as we now call it, carries an amount of energy proportional to its frequency. High-frequency light, blue light, ultraviolet light, carries more energy per photon. Low-frequency light, red light, infrared light, carries less. This seems obvious to us now, but at the time, it was revolutionary. It suggested that at the quantum level, energy itself is quantized, parceled into specific portions rather than flowing continuously like a river. Think of it like this. Imagine a staircase instead of a ramp. On a ramp, you can stand at any height, halfway up, 3/4 of the way up, or anywhere in between. But on a staircase, you can only stand on specific steps. You can't stand between steps. At the quantum level, energy is like a staircase. It comes in specific steps, specific quanta. You can have one quantum of energy, or two, or three, but not 1.5. Not in its purest form anyway. This discovery led to a deep insight about temperature itself. Temperature, at the quantum level, is related to the average energy of the particles involved. But because energy comes in quanta, temperature becomes connected to these discrete energy levels. A hot object has particles in higher energy states, jumping between the higher steps of that staircase. A cold object has particles in lower energy states, settling on the lower steps. And as the temperature approaches absolute zero, particles settle into their lowest possible energy state, what's called the ground state. Now, here's where things get interesting. At very low temperatures, strange things start to happen. Particles begin to exhibit behaviors that seem impossible according to classical physics. For instance, they can tunnel through barriers they shouldn't be able to pass through. Imagine a ball rolling toward a wall. In our everyday world, if the ball doesn't have enough energy to go over the wall, it simply bounces back. But at the quantum level, a particle can sometimes pass right through the wall, appearing on the other side as if the barrier wasn't there. This is called quantum tunneling, and it's one of the most bizarre predictions of quantum mechanics. Yet it's been confirmed countless times through experiments. At extremely low temperatures, another phenomenon becomes apparent. Quantum entanglement becomes more pronounced and easier to observe. Entanglement is the peculiar situation where two or more particles become correlated in such a way that measuring one particle instantly affects the others, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light. Yet entanglement is real, and it's been demonstrated repeatedly in laboratories around the world. But we're interested in the opposite extreme. We're interested in what happens at very high temperatures, in the quantum regime. And here's something fascinating. As temperature increases, particles gain energy and become more excited. They jump to higher and higher energy states. They collide more violently. They behave more chaotically. At some point, the temperature becomes so high that the quantum effects become truly profound. The uncertainty principle. Heisenberg's famous principle that states we cannot simultaneously know both the position and momentum of a particle with perfect precision becomes increasingly important. Let's pause for a moment and think about what the uncertainty principle really means. It's not just a limitation of our measurement techniques. It's not like we could theoretically know the exact position and momentum of a particle if we had better instruments. Rather, it's a fundamental feature of reality at the quantum level. The more precisely you know where a particle is, the less precisely you can know how fast it's moving. The more precisely you know its momentum, the less precisely you can know its location. This isn't a flaw in nature, it's a feature. It's part of what makes the quantum world quantum. Now, imagine heating something up to higher and higher temperatures. As the temperature rises, particles move faster and more unpredictably. Their positions become less certain because they're moving around so much. According to the uncertainty principle, this means their momenta become more certain, more well-defined. But wait, if they're moving faster, shouldn't their momenta be less certain? This is where quantum mechanics gets truly subtle. The relationship between energy, temperature, and uncertainty is complex and delicate. At extremely high temperatures, particles have so much energy that they can create and destroy other particles. This is a prediction of quantum mechanics and relativity combined. If you have enough energy concentrated in a small space, you can spontaneously create new particles and antiparticles, which then annihilate each other and convert back into energy. This process is happening constantly in the early universe during those first microseconds after the Big Bang, when temperatures were extraordinarily high. Particle-antiparticle pairs are being created and destroyed in a cosmic dance of creation and annihilation. A physicist named Paul Dirac predicted this phenomenon in the late 1920s. He was exploring the equations of quantum mechanics combined with Einstein's special relativity, and he found something unexpected. For every particle, there should be an antiparticle, a companion with the same mass but opposite electrical charge. At the time, this was a wild prediction, but within a few years, Dirac's antimatter prediction was confirmed experimentally. Anti-electrons, called positrons, were discovered in cosmic rays, and we now know that antimatter is just as real as regular matter, though it's far rarer in our current universe. This brings us to a crucial concept. At sufficiently high temperatures, the distinction between different types of particles begins to blur. Particles and antiparticles can be created from pure energy. Different types of particles can transform into each other. The forces of nature themselves can behave differently than they do at lower temperatures. This is one reason why studying the early universe is so fascinating. It allows us to observe physics in regimes that are impossible to achieve on Earth, at least with our current technology. The large particle accelerators like the Large Hadron Collider are designed specifically to recreate these high-temperature conditions in controlled ways. Scientists smash particles together at nearly the speed of light, creating brief moments where the temperature is extraordinarily high. In these collisions, particles are created that normally only existed in the early universe. By studying these collisions, physicists learn about the fundamental nature of matter and energy, and they probe the limits of what we understand about physics. But there's a limit to what even the most powerful particle accelerators can achieve. They can simulate temperatures up to roughly 1 trillion Kelvin, a quadrillion times hotter than the surface of the Sun. But the Planck temperature is vastly hotter still, about 10 billion times hotter than what the best accelerators can produce. So we cannot directly create Planck temperature conditions in a laboratory. We can only theorize about what might happen at such extreme scales. You might wonder, why is there a temperature scale called the Planck scale anyway? Why do physicists believe there's something special about this particular temperature? The answer involves the fundamental constants of nature and the way they fit together. And to explain this, we need to talk about 3 of the most important constants in all of physics. The speed of light, Planck's constant, which describes the quantization of energy, and the gravitational constant. These 3 constants can be combined in a particular way to create a natural unit of temperature. This temperature scale is called the Planck temperature, and it emerges naturally from the structure of physics itself. The speed of light, denoted by the letter c, determines how fast light travels through vacuum, about 300,000 kilometers per second. Planck's constant, denoted by h, is a tiny number that appears throughout quantum mechanics. It's related to the minimum amount of energy that can be exchanged in quantum processes. The gravitational constant, denoted by g, determines the strength of gravity, how strongly masses attract each other. These 3 constants are fundamental to our understanding of physics. They're not derived from anything deeper, they're just given as features of the universe. When physicists combine these 3 constants in just the right way, multiplying and dividing them according to dimensional analysis, out pops the Planck scale. The Planck length is the fundamental unit of distance, roughly 10 to the minus 35 meters. The Planck time is the fundamental unit of time, roughly 10 to the minus 44 seconds. And the Planck temperature is the fundamental unit of temperature, roughly 10 to the 32 Kelvin. These scales represent the boundary where quantum gravity effects become important, where we can no longer ignore the quantum effects of gravity. As we've journeyed through the quantum realm and its relationship to temperature, we've begun to see that temperature at extreme scales connects to deep questions about the nature of reality itself. It's not just a measure of thermal motion anymore. It's intimately connected to quantum uncertainty, to the creation and destruction of particles, to the fundamental constants that govern the universe. And as we move into the next section, we'll explore what happens when we try to combine quantum mechanics and gravity, the frontier that leads us directly to the Planck temperature and to some of the deepest mysteries in physics. Now we arrive at one of the great frontiers of theoretical physics, a place where 2 of the most successful theories ever created begin to clash with each other. Let's talk about what happens when the universe becomes so hot, so dense, that both quantum mechanics and gravity become equally important. This is the domain of quantum gravity, and it's where the Planck temperature truly matters. For most of the 20th century, physicists operated quite comfortably with 2 separate theories. Quantum mechanics governed the behavior of atoms, electrons, photons, and all the particles that make up matter and light. General relativity, Einstein's theory of gravity, governed the behavior of massive objects, planets, stars, and galaxies, the large-scale structure of space and time itself. These 2 theories worked beautifully in their respective domains. They made predictions that matched experiments with astounding precision. But they had a problem. They couldn't both be right in the same place at the same time. Think of it like this. Imagine 2 different maps of the same territory. each perfect and accurate, but contradicting each other about what's actually there. You can use one map to navigate the city streets, and it works perfectly. You can use another map to navigate the highways, and it also works perfectly. But if you try to use both maps simultaneously in the same location, they give conflicting information. You can't reconcile them. This is the situation physicists face with quantum mechanics and general relativity. The incompatibility between these two theories becomes critical at what's called the Planck scale. At distances smaller than the Planck length, smaller than roughly 10 to the minus 35 meters, and at times shorter than the Planck time, the quantum effects of gravity become so pronounced that they can't be ignored. At these scales, space-time itself becomes quantized, pixelated, broken into discrete chunks, or at least, that's what many physicists suspect. The truth is, we don't really know what happens at the Planck scale. We're in the realm of speculation informed by deep theory, but not yet confirmed by experiment. One of the most fascinating implications of this is that at the Planck temperature, space and time might not be smooth and continuous as they appear to be at larger scales. Instead, they might be grainy and discrete, like the pixels on a computer screen. If you zoom far enough into the fabric of space-time, far enough to see the Planck scale, you might find that space isn't infinitely divisible. There might be a smallest possible distance, a smallest possible interval of time. Everything smaller than this would be meaningless, not just practically, but in principle. This idea is rather strange when you first encounter it. Our everyday experience tells us that space and time are continuous and smooth. You can move a quarter inch, or an eighth of an inch, or a 16th of an inch. There's no limit to how precisely you can measure position. But quantum gravity suggests this might be an illusion. At the deepest level, space and time might be quantized, like energy is quantized in quantum mechanics. Just as energy comes in discrete packets called quanta, space and time might come in discrete packets as well. Let's pause for a moment and think about what this would mean. If space-time is quantized, then the universe isn't infinitely divisible. There's a smallest possible size, a smallest possible duration. Some physicists have speculated that at the Planck scale, the very concept of a point in space and time breaks down. A point at the Planck scale isn't really a point. It has a finite size and duration. It's a tiny cell of space-time, a quantum of space and time. This has profound implications for how we think about the structure of reality. Now, the Planck temperature is the temperature at which these quantum gravity effects would completely dominate. At the Planck temperature, the thermal energy of particles, the energy they have purely from their motion and heat, becomes comparable to the gravitational energy of those same particles. In other words, their heat becomes as important as their gravity. This is an extraordinary situation. Normally, gravity is an incredibly weak force. It takes an enormous mass to produce significant gravitational effects. But at the Planck temperature, gravity becomes strong enough to directly interact with quantum phenomena. To understand this better, let's think about what physicists call the coupling constant for gravity. This is a number that describes how strongly gravity interacts with matter. It turns out that this coupling constant is incredibly small. Gravity is about 40 orders of magnitude weaker than electromagnetism, the force that holds atoms together and produces chemistry. This is why gravity seems so weak in our everyday experience. Even the entire mass of the Earth is barely enough to hold us gently to its surface. But at the Planck scale, at the Planck temperature, this weakness disappears. Gravity becomes strong. It becomes comparable in strength to the other fundamental forces. This is why the Planck temperature is so significant. It's not just an arbitrary temperature. It's the temperature at which gravity stops being negligible and becomes a dominant force. It's the temperature at which the quantum effects of gravity become unavoidable. And because we don't yet have a complete theory of quantum gravity, a theory that successfully unifies quantum mechanics and general relativity, we can't reliably make predictions about what happens at or above the Planck temperature. Several theories have been proposed to solve this problem, to create a unified theory of quantum gravity. One of the most prominent is string theory, which suggests that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. In string theory, a particle is just a particular vibration pattern of a string, like a note played on a cosmic guitar. Different vibration patterns correspond to different particles. One of the nice features of string theory is that it naturally includes gravity. When you work out the mathematics, gravity emerges automatically from the theory, without having to add it in by hand. Another approach is loop quantum gravity, which tries to quantize space and time directly. In loop quantum gravity, space-time is woven from tiny loops, creating a discrete network of space and time. It's a beautiful approach, quite different from string theory, and it also naturally includes gravity. There are other approaches as well: asymptotic safety, causal dynamical triangulation, and others, each with its own virtues and challenges, but none of them has yet been definitively proven correct. The truth is, we simply don't know which approach, if any, correctly describes quantum gravity. This uncertainty about the nature of quantum gravity is one of the deepest open questions in physics. It's a frontier where we know our current theories break down, but we're not yet sure what lies beyond. And this frontier is intimately connected to the Planck temperature. If we could understand quantum gravity, we could understand what happens at the Planck temperature. And conversely, if we could somehow observe or measure something at the Planck scale, it would teach us about quantum gravity. But here's the challenge. The Planck scale is extraordinarily small, and the Planck temperature is extraordinarily high. We have no way to directly observe these scales with current technology. The best particle accelerators in the world can probe scales that are about 1 trillion times larger than the Planck length. To observe the Planck scale directly, we'd need a particle accelerator roughly the size of a galaxy. It's simply not practical. So physicists have to be creative. They look for indirect evidence. They study the early universe, where conditions were extremely hot and might have approached Planck-scale physics. They look for gravitational waves, ripples in space-time itself, which might carry information about quantum gravity. And they continue to develop new theories and test them against whatever observations they can make. One particularly intriguing possibility involves black holes. A black hole, you might recall, is an object so dense and so massive that nothing, not even light, can escape from inside its event horizon, the point of no return. A black hole has a certain mass, and associated with that mass is a temperature. This temperature was predicted by Stephen Hawking in 1974, and it's called the Hawking temperature. Here's the remarkable thing. The smaller a black hole is, the hotter its Hawking temperature. A supermassive black hole at the center of a galaxy has a Hawking temperature of only a tiny fraction of a Kelvin. But a tiny black hole, one with the mass of, say, a mountain, would have a Hawking temperature of billions of Kelvin. Now imagine a black hole that's even tinier, one with mass around the Planck mass, which is roughly the mass of a grain of sand compressed to Planck scale density. Such a black hole would have a Hawking temperature around the Planck temperature. And at that point, the black hole would be in an extraordinary state. It would be emitting radiation so intensely that it would evaporate almost instantaneously. The relationship between black holes and temperature becomes absolutely critical at Planck scales, which brings us to our next exploration. You might think that temperatures at the Planck scale only existed in the distant past, in the first instant after the Big Bang, and that's probably true for the universe as a whole. But black holes, as we'll explore more gently in the next section, might allow us to indirectly probe these extreme regimes. They might hold clues to quantum gravity that we haven't yet fully understood. And they remind us that the universe contains phenomena so strange, so extreme, that they force us to question our most fundamental assumptions about the nature of reality. As we've journeyed through the collision between quantum mechanics and gravity, we've seen that the Planck temperature isn't just a random number. It emerges naturally from the fundamental constants of physics. It represents a boundary, a frontier, where our current understanding breaks down. It's a place where space and time themselves might cease to be smooth and continuous. It's where gravity stops being weak and becomes strong. And it's a reminder that for all we've learned about the universe, there remain profound mysteries waiting at the deepest scales of reality. In the next section, we'll explore how black holes connect to this extreme temperature regime and what their properties tell us about the limits of heat and energy in the universe. Now we arrive at one of the most remarkable discoveries of 20th century physics, a discovery that connected black holes, those mysterious objects at the edge of our understanding, to temperature itself. Let's talk gently about black holes and the extraordinary phenomenon that Stephen Hawking predicted in 1974. This discovery changed everything we thought we knew about black holes and their relationship to thermodynamics and heat. For decades after black holes were first theoretically predicted, physicists thought of them as truly black, absolute sinks of darkness from which nothing could ever escape. According to general relativity, once something crosses the event horizon of a black hole, it's gone forever. It falls toward the singularity at the center and is crushed beyond recovery. This picture suggested that black holes were, in a sense, thermodynamic dead zones. They had no temperature. They absorbed everything, but gave nothing back. They violated the laws of thermodynamics, those fundamental rules that govern heat and energy throughout the universe. But then Hawking had a profound insight. He realized that when you consider quantum mechanics in the vicinity of a black hole's event horizon, something extraordinary happens. The boundary of a black hole isn't perfectly impenetrable to quantum effects. Virtual particle-antiparticle pairs, particles that briefly pop into existence and then annihilate each other, can sometimes be created right at the event horizon. If one particle of the pair falls into the black hole, while the other escapes to infinity, the escaping particle becomes real, carrying energy away from the black hole. From a distance, it looks as though the black hole is radiating energy into space, as though it has a temperature and is emitting heat like any warm object. Think of it like this. Imagine a bank's vault with an impenetrable door. Nothing can get in or out, you might think. But if you look very closely at the hinges of the door with a quantum microscope, you find that virtual coins are constantly appearing and disappearing. Sometimes, just by chance, a coin appears right at the hinge, and one half falls into the vault, while the other half escapes to the outside. From a distance, it looks as though the vault is leaking coins, even though nothing should be able to escape. This is roughly analogous to what happens with black holes and quantum particles at the event horizon. Hawking calculated what the temperature of this radiation should be, and the result was both beautiful and surprising. The temperature of a black hole's Hawking radiation depends on the black hole's mass. Remarkably, smaller black holes are hotter. A supermassive black hole, the kind found at the center of galaxies with millions or billions of times the mass of our Sun, has a Hawking temperature of only a tiny fraction of a Kelvin, colder than the cosmic microwave background. But a small black hole, one with the mass of a mountain, would have a Hawking temperature of millions of Kelvin. And if you could somehow create a black hole the size of an atom, it would have a temperature of billions of Kelvin. This inverse relationship between mass and temperature is counterintuitive. In our everyday experience, smaller things and larger things don't behave so differently in terms of temperature. But in the quantum realm, especially when gravity is involved, this relationship emerges naturally from the mathematics. It's one of those moments in physics where the equations tell us something our intuition never would have guessed, and it points towards something deeper, something that connects black holes, thermodynamics, and the fundamental structure of space-time itself. Now, here's where things get truly fascinating. If we extrapolate this relationship to its extreme, we can imagine a black hole with mass equal to the Planck mass, roughly 10 to the negative 8 kilograms, or about a billionth of a gram. Such a black hole would be extraordinarily tiny, about the size of the Planck length, 10 to the negative 35 meters, and its Hawking temperature would be approximately the Planck temperature. This is not a coincidence. This connection between Planck scale black holes and the Planck temperature is one of the deepest hints we have about quantum gravity. Let's pause for a moment and absorb what this means. At the Planck scale, a black hole would be as hot as it's possible for anything to be. The radiation it emits would be so intense, so energetic, that the black hole would evaporate almost instantaneously. It would exist for only about 1 Planck time, 10 to the minus 44 seconds, before disappearing completely. This is an almost incomprehensibly brief duration. For comparison, light would travel only 1 Planck length in 1 Planck time. These are the smallest meaningful durations and distances in physics. This raises a profound question. What happens at the moment of the Big Bang? The universe is believed to have been extraordinarily hot and dense at its birth. Some physicists speculate that the very first instant of the universe, before the first Planck time, might have involved quantum gravity effects, might have involved physics so extreme that it approached or even exceeded the Planck temperature. In those first infinitesimal moments, the entire universe might have been a roiling sea of quantum fluctuations, virtual particles, and virtual black holes appearing and disappearing at scales too small to imagine. One speculative idea proposed by some physicists is that the Big Bang itself might have been triggered by the evaporation of a primordial black hole, a black hole created during an earlier universe or phase. If the very first moment of our universe involved Planck-scale physics, with temperatures approaching the Planck temperature, then our universe's birth would have been intimately connected to quantum gravity. It would have emerged from conditions where space, time, gravity, and quantum mechanics were all equally important, all equally relevant to understanding what was happening. But let's step back from speculation and focus on what we can more reliably understand. The relationship between black holes and temperature tells us something important about the fundamental nature of black holes themselves. A black hole isn't really a hole at all, in the sense of being empty. It's an object with thermodynamic properties, with entropy, a measure of disorder or information content. This was discovered by Jacob Bekenstein, who realized that black holes must have entropy proportional to the area of their event horizon. The larger the black hole's surface area, the more entropy it has. This discovery led to a profound realization. Black holes have internal structure at the quantum level. They're not smooth and featureless as we might have thought. They have microstates, different quantum configurations that correspond to the same macroscopic black hole. The entropy of the black hole counts the number of possible microstates, just as entropy in thermodynamics counts the number of ways atoms can be arranged in a system. This connects black holes deeply to information theory and raises fascinating questions about what happens to information that falls into a black hole. Does it truly disappear forever, or is it somehow preserved in the quantum structure of the black hole? These questions remain open and are actively studied by physicists today. The relationship between black holes, thermodynamics, and quantum information is one of the most active and exciting areas of theoretical physics. Some researchers believe that this relationship holds the key to understanding quantum gravity. They argue that if we can fully understand the thermodynamic properties of black holes, we might be able to decode the principles of quantum gravity and perhaps even glimpse what happened at the Planck scale in the very early universe. Now, let's think about what the existence of the Planck temperature means in practical terms. It means there's a maximum possible temperature that anything can have. You can't heat something hotter than the Planck temperature, at least not in any meaningful sense. If you tried, something would go wrong. Space and time would become corrupted. The object might collapse into a black hole, or something else entirely might happen, something we don't yet understand, because we don't yet have a complete theory of quantum gravity. Some physicists have speculated about what might happen if you tried to heat something to exactly the Planck temperature. Would you create a tiny black hole? Would space and time break down? Would new physics emerge, physics that violates everything we think we know? The truth is, We don't know. But the Planck temperature represents a hard ceiling, a fundamental limit that nature appears to enforce. And this limit is deeply connected to the quantum properties of gravity, to the structure of spacetime itself, and to the nature of black holes. Interestingly, this limit also connects to something called holography. The holographic principle, proposed by Juan Maldacena and others, suggests that a three-dimensional system, like our universe, might be equivalent to a two-dimensional system on its boundary. It's a bit like how a hologram contains all the information of a three-dimensional object on a two-dimensional surface. If the holographic principle is correct, it would profoundly change how we understand the structure of space and the nature of reality. And the relationship between black holes, temperature, and quantum gravity would be central to this understanding. You might wonder, if black holes can have such extreme temperatures, and if the Planck temperature represents an absolute ceiling, are there black holes that have actually reached the Planck temperature? Could there be Planck mass black holes in existence right now? The answer is probably no. Such black holes would evaporate almost instantaneously through Hawking radiation. They would have existed, if at all, only in the earliest moments of the universe, when temperatures were extraordinarily high. Any Planck mass black holes created after that initial moment would evaporate almost immediately, so we're unlikely to ever encounter one. But the possibility of Planck mass black holes and the physics associated with them is important for our understanding of the early universe. It's a reminder that at the highest temperatures and smallest scales, the universe becomes a place where quantum mechanics and gravity dance together in ways we're only beginning to understand. And it's a beautiful example of how theoretical physics works. We make predictions about exotic phenomena. We explore their implications, and gradually, we build a deeper understanding of how the universe works, even if we can never directly observe the most extreme regimes. As we've explored black holes and their relationship to temperature, we've seen that the Planck temperature isn't just a theoretical limit. It's intimately connected to the structure of black holes, to the very nature of gravity at quantum scales, to thermodynamics and information theory. It emerges from the deep mathematics of physics and points toward principles we haven't yet fully grasped. In the next section, we'll take a step back and explore what modern observations from NASA, ESA, and telescopes like JWST have taught us about extreme temperatures in the universe, and how these observations help us understand the Planck temperature from a more empirical angle. Now let's gently shift our perspective and look at what astronomers and physicists have actually observed in the universe. For all our theoretical discussions about the Planck temperature and the extreme physics at the smallest scales, we must ground our understanding in real observations. We must ask, what does the universe actually show us about heat and temperature? What have instruments like those aboard NASA spacecraft, the European Space Agency's telescopes, and the James Webb Space Telescope revealed about the hot universe? These observations provide a reality check for our theories and help us understand where the Planck temperature fits into the actual cosmos. Let's begin with what we observe in the present universe. When we look out at space with telescopes, we see objects at various temperatures. The coldest places are the vast stretches between galaxies, where dust clouds and sparse gas drift in the darkness. These regions hover just a few Kelvin above absolute zero, sometimes even lower. The cosmic microwave background, that ancient light from the early universe we discussed earlier, has a temperature of about 2.7 Kelvin. It's one of the coldest things we can observe in space. But there are also tremendously hot objects. The cores of stars are furnaces of incredible heat. The surface of our sun, at roughly 5,800 Kelvin, is hot enough to make it glow brilliant yellow. But inside the sun's core, where nuclear fusion takes place, temperatures reach about 15 million Kelvin. This heat, created by the fusion of hydrogen into helium, is what makes the sun shine and gives life to everything on Earth. The sun, in a sense, is our window into understanding high-temperature physics. It's a natural nuclear reactor, a place where matter behaves in ways that we can study and learn from. But the Sun is only moderately hot by cosmic standards. Other stars can be far hotter. The cores of the most massive stars reach temperatures of hundreds of millions of Kelvin. And when these massive stars die, they can create extraordinary phenomena. A supernova explosion, the violent death of a star, releases temperatures in the billions of Kelvin. For a brief moment, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. These explosions are so bright and so powerful that they can be seen from billions of light years away. And they're hot, incredibly, unimaginably hot. Let's pause for a moment and think about what happens in the aftermath of a supernova. The explosion creates a shock wave that races outward through space. Behind this shock wave, matter is compressed and heated to extreme temperatures. Depending on the supernova's properties, temperatures can reach tens of billions of Kelvin, sometimes even higher. In these conditions, nuclear fusion continues to occur. Elements heavier than iron are created. Gold, silver, platinum, uranium, the heavy metals that make up much of the matter in our world, are created in these stellar furnaces during supernova explosions. Every atom of gold in a wedding ring was once forged in the heart of a dying star. The observation of supernova remnants from space telescopes has taught us a great deal about high-temperature physics. NASA's Chandra X-ray Observatory, for instance, can observe the hot gas in supernova remnants by detecting X-rays, high-energy radiation emitted by gas heated to millions of Kelvin. These observations reveal the structure of the explosion, show us how the energy is distributed, and help us test our theoretical models of stellar death and elemental creation. But there are even hotter phenomena. When black holes actively feed on material from companion stars, they create what's called an accretion disk, a swirling disk of matter spiraling down toward the black hole. The friction in this disk heats the material to millions of Kelvin, and sometimes to even higher temperatures. Material in the inner regions of accretion disks around black holes can reach tens of billions of Kelvin. Some of this material is funneled away from the disk and escapes in powerful jets that shoot out from near the black hole at nearly the speed of light. These jets can extend for thousands or even millions of light years, carrying enormous amounts of energy across intergalactic distances. Observations of these jets and accretion disks, made by various space telescopes including the European Space Agency's XMM Newton Observatory and NASA's SWIFT satellite, have revealed the extraordinary power of black holes and the extreme temperatures they can create. Yet even these temperatures, billions or tens of billions of Kelvin, are still vastly cooler than the Planck temperature, which is roughly 10 billion 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 times hotter. Now let's turn our attention to the early universe, where we expect to find the hottest temperatures that have ever existed. We can observe the early universe indirectly through several methods. The most direct is through the cosmic microwave background, that ancient light we discussed earlier. But we can also look at the light from the first galaxies, the light that has been traveling toward us since the universe was only a few 100 million years old. The James Webb Space Telescope, launched in 2021, has been revolutionizing our understanding of these early galaxies. JWST observes the universe primarily in infrared light, allowing it to see through dust and to detect light from very distant, very young galaxies. These galaxies existed when the universe was hot, when the background temperature was much higher than it is today. By studying these galaxies, by measuring their light and analyzing its properties, astronomers can infer conditions in the early universe. We learn about the density of matter, the rate at which the universe was expanding, and the temperature of the radiation that filled space at that time. From such observations, combined with theoretical models and data from other sources, astronomers can trace the universe's temperature history. At 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. At 1,000th of a second after the Big Bang, it was about 1 trillion Kelvin. At 1 millionth of a second, it was about a quadrillion Kelvin. The trend is clear. Go back in time, and the temperature rises exponentially. Go back far enough, and you approach temperatures that become increasingly difficult to comprehend. But there's a limit to how far back we can reliably trace this history. Our current theories of physics, which combine quantum mechanics and general relativity at lower energies with the standard model of particle physics, break down at some point in the early universe. That point is approximately the time when the universe was 1 Planck time old, 10 to the minus 44 seconds. At that moment, if our theories are correct, the temperature would have been approximately the Planck temperature. Beyond that point, we enter a regime where quantum gravity effects are so dominant that we can no longer use our current theories to make predictions. This is one of the most profound limitations in our current understanding of the universe. We can observe the universe back to about 380,000 years after the Big Bang, when the cosmic microwave background was released. We can theoretically extrapolate backward to about 1 second after the Big Bang with reasonable confidence, using particle accelerator experiments to validate our predictions at intermediate temperatures. But beyond that, the physics becomes increasingly speculative. We can discuss what might have happened in the first microsecond after the Big Bang, but we do so with increasing uncertainty. And when we try to discuss what happened in the first Planck time, we're essentially at the edge of what we can meaningfully theorize about. ESA observations and data from various missions have helped scientists map out this early universe timeline. Missions like WMAP and the Planck satellite, named after Max Planck, the same physicist whose constant we discussed earlier, have provided precise measurements of the cosmic microwave background, which encode information about the universe's conditions in the early moments after the Big Bang. By analyzing tiny temperature fluctuations in this ancient light, variations of only a few millionths of a Kelvin, scientists can determine the universe's composition, age, and expansion history. What's particularly remarkable is that these observations confirm that the universe did indeed begin hot and has been cooling ever since. They confirm that there was a Big Bang, a moment of creation when the universe sprang into existence in an extraordinarily hot state. They provide evidence that supports our theoretical models of how the universe evolved from those first moments to the present day. Yet at the same time, these observations highlight the gap in our knowledge. They show us that physics beyond the Planck scale remains mysterious and inaccessible to us. One fascinating avenue of research involves looking for signatures of quantum gravity in the universe around us. Some physicists speculate that quantum gravity effects, though typically only important at the Planck scale, might occasionally leave subtle marks on our observable universe. For instance, they might affect the way light travels across cosmic distances, or they might create tiny distortions in the geometry of spacetime. If such effects could be detected, they might provide indirect evidence of quantum gravity and help us understand what happens at the Planck scale. Another avenue involves studying gravitational waves, ripples in spacetime itself. When massive objects like black holes or neutron stars collide, they create gravitational waves that propagate outward at the speed of light. These waves were first detected directly by the LIGO Observatory in 2015, confirming Einstein's predictions. The discovery of gravitational waves opened a new window on the universe. Now we can observe not just light from distant objects, but gravitational waves, giving us a new way to probe the universe's most violent and energetic phenomena. Some physicists hope that studying gravitational waves might eventually provide clues about quantum gravity and the Planck scale. Let's take a breath here. We've journeyed through observations of hot phenomena in the present universe, from supernovae to black hole accretion disks, and we've traced the universe's temperature history backward in time toward its creation. We've seen that observations confirm the theoretical framework we've been discussing, while also showing us the limits of our current knowledge. The Planck temperature remains beyond what we can directly observe, but the convergence of theory and observation gives us confidence that we're asking the right questions and moving in a productive direction. Yet there remains something humbling in all of this. We can theorize about the Planck temperature, We can calculate what it should be based on fundamental constants of nature. We can understand why it represents a limit, but we cannot directly observe it. We cannot create it in a laboratory. We can only infer its existence and significance from the mathematics of quantum gravity and from observations of the universe at more accessible temperatures. This is the nature of frontier physics. We must use reason and observation to probe beyond the boundaries of direct experience, always aware that our understanding is provisional and subject to revision as we learn more. In the next section, we'll explore what happens to the early universe as it cools down from these extreme temperatures. We'll see how the physics changes, how new phenomena emerge, and how the universe gradually transformed from a hot, featureless soup of particles into the complex, structured cosmos we observe today. We'll trace this journey gently through the various epochs of cosmic history, understanding how temperature shaped everything that followed. Now we turn our attention to one of the most profound narratives in all of science, the story of how the universe has cooled over the past 13.8 billion years. It's a story written in the temperature of light and matter, a story where each decrease in temperature marks a threshold where new physics becomes possible and new structures emerge. Let's trace this journey gently, watching as the universe transforms from a state of almost incomprehensible heat into the rich, complex cosmos we inhabit today. Imagine the universe at the very first moment we can meaningfully discuss, at 1 Planck time after the Big Bang, roughly 10 to the minus 44 seconds. At this moment, if our theories are correct, the temperature would have been approximately the Planck temperature. What would the universe look like at this moment? The honest answer is, we don't really know. Our physics breaks down. Space and time themselves become fuzzy and uncertain. The distinction between different types of particles becomes meaningless. Gravity and quantum mechanics dance together in ways we haven't yet learned to describe mathematically. But we can describe what happens as the universe expands and cools from that point forward. At about 10 to the minus 36 seconds, still unimaginably early, still infinitesimally small, the temperature had dropped to perhaps 10 to the 28 Kelvin. At this moment, according to some theories, the universe underwent a dramatic transition called inflation. During inflation, the universe expanded exponentially, not gradually, but at an accelerating rate. It doubled in size not once, not twice, but perhaps 100 times or more in a fraction of a second. This inflation smoothed out the universe, removing any wrinkles or irregularities that might have existed earlier. Let's pause for a moment and think about what inflation means. Imagine taking a wrinkled balloon and blowing it up to an enormous size. As it inflates, the wrinkles get stretched out and flattened, becoming so tiny and subtle that you can no longer see them. This is what inflation did to the universe. It took any initial irregularities and stretched them out so much that the universe appeared perfectly smooth and uniform on large scales. But it didn't make the universe perfectly smooth everywhere. Quantum fluctuations, tiny, random variations inherent to the quantum nature of reality, were also stretched out. These stretched quantum fluctuations became the seeds of all the galaxies and galaxy clusters we see today. Every galaxy we observe is descended from a quantum fluctuation that was expanded to macroscopic size by cosmic inflation. As we continue tracing the universe's cooling journey, we move forward to about 1 microsecond after the Big Bang. By this time, the temperature had dropped to roughly 1 trillion Kelvin. At this temperature, the strong nuclear force, the force that holds protons and neutrons together, becomes distinct and important. Before this point, at even higher temperatures, the strong force was unified with the other fundamental forces in a way we don't yet fully understand. But at around 1 trillion Kelvin, the strong force separates out. Protons and neutrons, which were constantly being created and destroyed in the particle-antiparticle dance, begin to become stable. They start to stay around rather than immediately annihilating with their antiparticles. As we move forward to about 3 minutes after the Big Bang, the temperature has dropped to roughly 1 billion Kelvin. At this point, something crucial happens. nucleosynthesis begins. Protons and neutrons, now relatively stable, begin to fuse together to form the nuclei of light elements. Hydrogen nuclei, single protons, are the most common, but some protons and neutrons combine to form deuterium, which is heavy hydrogen. Some form helium-3, some form helium-4, the more common isotope of helium, and tiny amounts of lithium and beryllium are created as well. This process, known as Big Bang nucleosynthesis, happens only in the first few minutes after the Big Bang, before the universe cools below about 100 million Kelvin and the density drops too much for fusion to continue. The remarkable thing about Big Bang nucleosynthesis is that it makes predictions about the abundances of light elements that we can test through observation. When we measure the amounts of hydrogen, helium, deuterium, and lithium in the universe today, we find that they match the predictions of Big Bang nucleosynthesis remarkably well. This is one of the strongest pieces of evidence that the Big Bang actually happened and that the early universe was indeed hot and dense. It's beautiful confirmation that our theoretical models capture something real about the universe's history. Now we leap forward in time, past several 100,000 years, to about 380,000 years after the Big Bang. By this point, the temperature has dropped to roughly 3,000 Kelvin. At this temperature, something profound occurs: recombination. Electrons, which had been free-floating in a hot plasma, suddenly have low enough energy that they can bind to atomic nuclei. Hydrogen atoms form. Helium atoms form. For the first time, neutral atoms exist in abundance. And when neutral atoms form, something else happens. The universe becomes transparent to light. Before recombination, the universe was opaque, like being inside a thick fog. Photons, particles of light, were constantly being created and absorbed by the free electrons. Light couldn't travel far without being scattered. But after recombination, when atoms form and electrons are bound up inside them, the photons can travel freely. The universe suddenly becomes transparent. The light that was trapped gets released, streaming across space in all directions. This ancient light is what we observe today as the cosmic microwave background. When we observe the CMB, we're looking back at the universe as it was 380,000 years after the Big Bang, when it was about 3,000 Kelvin, roughly as hot as the surface of a cool red dwarf star. This moment, 380,000 years after the Big Bang, is the earliest time we can directly observe with light-based telescopes. We cannot see earlier than this with photons, because before recombination, photons were trapped. But we might be able to see earlier with other methods. Gravitational waves, for instance, could in principle carry information from even earlier times, and future observations might reveal signatures of phenomena that happened before recombination. As we continue forward from recombination, the universe continues to expand and cool. For hundreds of millions of years after recombination, the universe contained no stars, no galaxies, just vast clouds of neutral hydrogen and helium gas, cooling gradually as the universe expanded. But these clouds were not perfectly uniform. They had tiny density variations inherited from those quantum fluctuations that inflation had stretched to macroscopic size. Gravity amplified these variations. Where density was slightly higher, gravity pulled material inward, creating increasingly dense clumps. Over hundreds of millions of years, these clumps grew denser and hotter until eventually they became hot enough for fusion to ignite. The first stars were born. The temperature inside these first stars reached millions of Kelvin in their cores, hot enough for hydrogen fusion. And as stars form and die, some of them explode as supernovae, enriching the surrounding gas with heavier elements created in their cores. Subsequent generations of stars and galaxies formed from this enriched material. And eventually, about 4.6 billion years ago, our Sun formed from such material, a third or fourth generation star containing heavy elements like carbon, oxygen, nitrogen, and iron that had been created in earlier stars. Let's pause and absorb the narrative we've just traced. The universe began at the Planck temperature, a heat so extreme that our current physics cannot describe it. As it expanded, it cooled. Different physical regimes became possible at different temperatures. Particle physics, nuclear fusion, the formation of atoms, the formation of stars and galaxies, all of these emerged as the universe cooled to progressively lower temperatures. The universe, in a sense, has been gradually transitioning from a state of simple, extreme heat to increasingly complex, structured coolness. And this cooling process has allowed everything we see today, from stars to planets to life itself, to emerge and flourish. This narrative also highlights why the Planck temperature is so significant. It's not just a theoretical curiosity. It represents the point beyond which our current understanding of physics cannot extend. The universe passed through all these different temperature regimes, all these different epochs, starting from a condition hotter than the Planck temperature, or at least, starting from a condition that rapidly cooled from such temperatures. Understanding what happened at the Planck temperature and higher is essential to understanding the universe's true origin. It's the frontier where we need new physics, a theory of quantum gravity that doesn't yet exist. Some physicists have proposed speculative ideas about what happens before the Planck time. Perhaps the universe didn't truly begin at the Planck time, but existed in some pre-Big Bang state before that. Perhaps time itself began at the Planck time. Perhaps the universe is eternal, with infinite cycles of Big Bangs and Big Crunches. Perhaps there are other universes, a multiverse, with different physical laws and initial conditions. These ideas remain highly speculative, but they show the way physicists are thinking about the deepest questions. They remind us that while we've learned an enormous amount about the universe's history, profound mysteries remain. Another perspective comes from thermodynamics and the second law. The second law of thermodynamics states that entropy, disorder, randomness, tends to increase over time. The universe began in an extraordinarily ordered state. All the matter and energy concentrated in an incredibly hot, incredibly dense region. As the universe expanded and cooled, this initial order has gradually been converted into disorder. Energy has spread out. Matter has become less organized. Yet paradoxically, out of this increase in overall disorder, local structures of increasing complexity have emerged: stars, galaxies, planets, and life. How is this possible? The answer is that these local structures are only possible because they're supported by an even greater increase in disorder elsewhere. Life and complexity are permitted, in a sense, as the universe tends toward its ultimate fate of maximum disorder and entropy. This brings us to a philosophical point worth considering. The Planck temperature represents not just a physical limit to how hot things can get, but also a limit to how ordered and concentrated the universe's energy could possibly be. No structure could be more concentrated, more ordered, more extreme than the state of the universe at the Planck temperature. Everything that has happened since, every galaxy, every star, every planet, every life form, has unfolded as the universe has relaxed from that state of maximum extremeness towards states of increasing disorder and complexity. In a very real sense, all of cosmic history is the story of the universe cooling down from an initial state at the Planck temperature. You might wonder, will the universe continue cooling forever? The answer, surprisingly, may be no. Current observations suggest that the universe's expansion is actually accelerating, driven by a mysterious form of energy called dark energy. If the universe continues to accelerate in its expansion, it will cool more and more slowly, asymptotically approaching a temperature of absolute zero, but never quite reaching it. The universe will fade into darkness. First, the stars will burn out, then galaxies will dissolve, then eventually even atoms might decay. The universe would end in what's called a heat death, a state of maximum entropy where no structures exist and no processes occur. It's a sobering vision of the distant future, but it flows naturally from the physics we understand today. As we've journeyed through the early universe's cooling history, we've seen how temperature shaped everything, how it determined what physics was possible, what structures could form, and ultimately, how it led to the universe we inhabit today. We've traced the path from the incomprehensible extremity of the Planck temperature down through billions of years of cooling to the cold, complex universe we observe. And we've glimpsed the far future, where the universe continues its slow cooling toward an ultimate state of darkness and disorder. The Planck temperature stands at the beginning of this story, a boundary marking the limit of what we can currently understand, and the frontier where new physics awaits discovery. In the next section, we'll step back and think about the fundamental limits and mysteries that remain. We'll explore open questions. What lies beyond the Planck temperature? What does quantum gravity tell us about the deepest structure of reality? And how might future discoveries reshape our understanding of these extreme regimes? Now we arrive at the frontier, the place where our current theories reach their limits and profound mysteries await us. Let's explore gently what lies beyond the Planck temperature, what we don't yet know, and what questions physicists are still wrestling with as they work toward a deeper understanding of reality. This is territory where speculation merges with rigorous theory, where we acknowledge the boundaries of our knowledge while still probing thoughtfully at what might lie beyond. The fundamental mystery is this: what happens at temperatures above the Planck temperature? Our current theories, quantum mechanics and general relativity, cannot tell us. They break down. The mathematics becomes undefined. Infinities appear where finite answers should be. This breakdown is not a failure of mathematics or physics, but rather a message from nature. It's telling us that we're asking questions in a domain where our current frameworks no longer apply. We need something new. We need a theory of quantum gravity. Several approaches to quantum gravity have been proposed, as we briefly discussed earlier. String theory suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. In this theory, what we perceive as particles, electrons, photons, quarks, are actually different vibrational modes of strings. An electron is one pattern of vibration. A photon is another. And importantly, one of the vibrational modes corresponds to the graviton, the quantum particle that mediates gravity. This elegant feature automatically includes gravity in string theory without having to add it in by hand as in other approaches. But string theory comes with a price. It requires additional spatial dimensions beyond the 3 we can directly observe. Most versions of string theory work in 10 or 11 dimensions, with the extra dimensions somehow curled up or compactified at scales too small for us to detect directly. It's a strange feature, and whether nature actually works this way remains unknown. String theory is extraordinarily mathematically elegant and has been developed extensively over the past several decades, yet it remains unconfirmed by direct experiment. No string has ever been observed. No signature of extra dimensions has been definitively detected. Some physicists view this as a profound limitation. Others argue that string theory is so mathematically consistent and elegant that it's likely to be pointing us toward truth, even if experimental confirmation remains out of reach for now. An alternative approach is loop quantum gravity. Rather than starting with strings, loop quantum gravity tries to quantize space and time directly, the way quantum mechanics quantizes energy. In this approach, space is woven from tiny loops, quantum threads of spacetime itself. These loops connect to form a network, and this network constitutes the fundamental fabric of space and time. At scales larger than the Planck length, space appears smooth and continuous, the way a coastline appears smooth from far away, but becomes jagged and fractal up close. But at Planck scales, the discrete, loopy structure becomes apparent. Loop quantum gravity is attractive because it doesn't require extra dimensions and remains closely tied to the principles of general relativity. However, It's more difficult to extract physical predictions from loop quantum gravity, and it hasn't yet achieved the same level of mathematical elegance and completeness as string theory. Both approaches remain active areas of research, with passionate advocates for each. The truth is, we don't yet know which approach, if either, correctly describes quantum gravity at the Planck scale. Let's pause and think about what it would mean if one of these theories turned out to be correct. If string theory is right, then at the Planck scale, tiny strings vibrate and oscillate, creating all the particles and forces we observe. If loop quantum gravity is right, then at the Planck scale, space and time themselves are woven from discrete loops. Both scenarios are breathtaking to contemplate. Both suggest that reality at its deepest level is far stranger and more exotic than our everyday experience suggests. But there's something even more fundamental we're uncertain about: the nature of time itself. In both general relativity and quantum mechanics, time plays a role, but the role is different in each theory. In relativity, time is intimately woven together with space into a four-dimensional fabric called spacetime. In quantum mechanics, time is more like a parameter that we use to describe how systems evolve. When we try to merge these theories, we encounter difficulties. Some physicists have speculated that time, as we know it, might not be fundamental. It might emerge from something more basic at the Planck scale. Perhaps at ultra-extreme temperatures, the notion of before and after becomes fuzzy or meaningless. Perhaps time itself has a quantum nature that we haven't yet understood. This raises a profound question. What happened before the Big Bang? If time itself emerged from quantum gravity effects, then asking what happened before the Big Bang might be like asking what's north of the North Pole. The question might not have a meaningful answer. Time might have begun with the Big Bang, or more precisely, the concept of beginning, and time might not apply in the regime before the Planck time. This is deeply strange to contemplate, but it flows naturally from taking quantum gravity seriously. Some physicists, like Stephen Hawking, have proposed that the universe might have no boundary in time, that spacetime is a closed, finite structure without beginning or end, only a history that curves smoothly. In this picture, the Big Bang isn't truly a beginning, but rather a boundary in imaginary time that becomes smooth when you approach it. Other physicists propose cyclic or bouncing universe models, where the Big Bang is preceded by a contraction phase, a big crunch, from an earlier universe. These models attempt to avoid the singularity and the breakdown of physics that occurs at the Planck scale. Each of these proposals has its virtues and challenges. Each attempts to answer the question, what lies beyond the Planck scale? What physics governs the regime where temperatures exceed the Planck temperature? But none of them has yet been proven correct. And that's the honest state of our knowledge today. We have theories and ideas, but we don't yet know which, if any, correctly describes the deepest levels of reality. Now you might ask, why should we care about all this? Why does it matter if we don't understand what happens at the Planck scale? The answer is that understanding the Planck scale is essential to understanding the universe's origin. If we want to know where the universe came from, how it began, what set the initial conditions, we need to understand quantum gravity and what happens at the Planck temperature. These aren't idle theoretical questions. They're questions about the most fundamental aspects of existence. There's also a practical reason to care. History shows that understanding the deep structure of physics has practical applications we couldn't have anticipated. A century ago, quantum mechanics seemed like an abstract intellectual exercise with no practical value. Yet quantum mechanics is the foundation of all modern technology. Semiconductors, lasers, nuclear energy, medical imaging. It's impossible to overstate its importance. Similarly, when we finally understand quantum gravity, it might revolutionize our technology in ways we can barely imagine today. Or it might not. But the pursuit of understanding is valuable in itself, regardless of practical applications. Let's consider another mystery. What is the relationship between thermodynamics and gravity at the Planck scale? We know that black holes have entropy and temperature. We know that the laws of thermodynamics seem to apply even to black holes. But the relationship between thermodynamics and gravity remains deeply mysterious. Some physicists believe that thermodynamics and gravity are not separate phenomena, but manifestations of a deeper principle. Perhaps gravity itself is an entropic force, a force that emerges from the tendency of systems toward maximum entropy, just as thermal forces emerge from the random motion of molecules. This idea, proposed by Eric Verlinde and others, suggests that gravity might not be fundamental, but emergent. Just as temperature emerges from the motion of countless atoms, gravity might emerge from the properties of information and entropy in a quantum system. If true, this would be revolutionary. It would mean that gravity isn't one of the fundamental forces of nature, but rather a consequence of more basic principles. This would represent a profound reshaping of how we understand the universe. Another mystery. What is dark energy? Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Something is pushing the universe apart, driving the acceleration. We don't know what this something is. We call it dark energy, but that's essentially a placeholder for our ignorance. Dark energy makes up about 70% of the universe's total energy density. It dwarfs all the matter and radiation combined. Yet we have almost no understanding of what it is or why it's there. Some physicists speculate that dark energy might be connected to quantum gravity effects at the smallest scales. Perhaps it's related to the vacuum energy of quantum fields, or perhaps it's a signal of physics beyond what we currently understand. And then there's dark matter. About 25% of the universe's mass energy content is in the form of dark matter, material that doesn't interact with light, that we can't see directly, but that we know exists because of its gravitational effects on galaxies and galaxy clusters. We don't know what dark matter is. It might be WIMPs, weakly interacting massive particles, or axions, or primordial black holes, or something we haven't yet imagined. Understanding dark matter is one of the grand challenges of modern physics, and it too might be connected to physics at extreme scales. These mysteries, quantum gravity, the nature of time, the origin of the Big Bang, dark energy, dark matter, form an interconnected web of unknowns at the frontier of physics. Solving one might illuminate the others, or they might remain mysterious for decades or centuries to come. This is the state of fundamental physics today. We understand an enormous amount. Our theories make predictions that agree with observations to remarkable precision. But there remain deep questions we cannot yet answer, domains where our current theories break down, frontiers we haven't yet crossed. The Planck temperature stands as a marker of this frontier. It's the temperature at which we know our current physics fails. It's a challenge and an invitation. It challenges us to develop new theories, new mathematical frameworks, new ways of thinking about the structure of reality. And it invites us to participate in one of humanity's greatest intellectual adventures, the quest to understand the universe at its deepest levels. Let's take a moment to breathe and absorb what we've discussed. We've acknowledged the boundaries of our knowledge. We've explored the leading theories attempting to transcend those boundaries. We've seen that the Planck temperature is not just a number, but a symbol of our current ignorance and a beacon pointing toward future discoveries. In a very real sense, everything we've explored in this journey, from basic thermodynamics to quantum mechanics to general relativity to the early universe, has been leading us to this frontier where new physics awaits. As we move toward the final sections of our journey together, we'll begin to step back and gain perspective. We'll think about what all of this means, not just scientifically, but philosophically. We'll consider the wonder and beauty in our understanding of the universe, while also appreciating the profound mysteries that remain. We'll acknowledge what we know with confidence, while also staying humble about how much we still don't understand. And we'll prepare ourselves to drift gently towards sleep, carrying with us the memory of this voyage to the edge of physics and beyond. Now, as we near the end of our journey, let's pause and reflect on what we've explored together. We've traveled from the familiar concept of heat and temperature, through quantum mechanics and general relativity, all the way to the Planck temperature and the frontier of our understanding. We've discussed theories and observations, mysteries and limits, but perhaps now is the time to step back and think about what all of this means, not just intellectually, but in a deeper, more contemplative way. There's something rather beautiful about the existence of limits. In a universe without boundaries, without thresholds, without ultimate constraints, our quest for understanding might be infinite and perhaps ultimately futile. But the Planck temperature represents something different. It represents a genuine limit, a frontier that nature itself has established. And the existence of this limit tells us something profound. The universe has a structure. It has principles that govern it. It has a deep order beneath the apparent chaos of phenomena. Consider what the Planck temperature represents from a philosophical perspective. It's not just the highest temperature that can exist. It's also, in a sense, the highest order of magnitude at which heat and temperature even have meaning in the way we typically understand them. Beyond the Planck temperature, our ordinary concepts of temperature and thermal energy break down. Space and time themselves become uncertain. The distinction between particles and fields becomes blurred. Reality at those scales is so profoundly different from our everyday experience that we struggle even to ask meaningful questions about it. Yet this limitation is also liberating. It tells us that we don't need to worry about infinities or physical impossibilities lurking at arbitrarily high temperatures. Nature has provided a built-in stopping point. There's a deepest level. There's a frontier we can aim toward. This gives focus and direction to our investigations. It suggests that a complete theory of physics, a final unified theory explaining everything, might exist, even if we haven't yet found it. Throughout history, humanity has discovered that the universe operates according to principles. We've learned that these principles can be expressed mathematically. We've found that nature loves simplicity and elegance, even when describing extraordinarily complex phenomena. The discovery of the Planck temperature fits into this pattern. It emerges naturally from the fundamental constants of nature: the speed of light, Planck's constant, the gravitational constant. These constants are woven together into a scale, a temperature, that represents a fundamental limit. This is the sort of deep order and elegance that physicists have come to expect and cherish. But alongside this sense of order and comprehensibility, there remains profound mystery. We don't yet have a complete theory of quantum gravity. We don't fully understand what happened at the moment of the Big Bang. We don't know the ultimate origin of the laws of physics themselves. Why does the universe obey the particular laws it does? Why these constants and not others? Why does anything exist at all rather than nothing? These are questions that physics alone might never answer. They gesture toward domains of inquiry, philosophy, metaphysics, perhaps even spirituality, that lie beyond the scope of science. This coexistence of deep understanding and persistent mystery is characteristic of science at any frontier. It's a delicate balance. On one hand, we've learned so much. We understand the structure of atoms. We understand how stars shine. We understand how galaxies form and evolve. We understand the history of the universe going back billions of years. We've decoded the genetic basis of life. These are achievements of tremendous magnitude. And yet, at the deepest level, we encounter mysteries we cannot yet solve. Perhaps this is as it should be. Perhaps a universe that was completely understood, completely transparent to human reason, would be less beautiful and less wonderful than one that always holds back some secrets. Perhaps the perpetual frontier, the endless mystery at the edge of knowledge, is what gives science and philosophy their meaning. We explore not because we expect to find final answers, but because the journey itself is valuable. Each answer we find opens up new questions. Each frontier we cross reveals new frontiers beyond. The Planck temperature in this light becomes more than just a number. It becomes a symbol of human curiosity, of our drive to understand the universe at the deepest possible level, and of the profound limits that nature has placed on that understanding. It's a reminder that we're not omniscient, that we're inhabitants of a universe far greater and more complex than our current theories can encompass. And there's something peaceful, something almost meditative, in acknowledging those limits. Let's think about this from another angle. The Planck temperature is unimaginably hot, roughly 10 to the 32 Kelvin, which is more than a billion times hotter than the surface of the Sun. Yet to the universe, at the moment of the Big Bang, this was not an extreme temperature. It was merely the ambient temperature of space. Particles and forces that would later separate and become distinct were unified at this temperature. The universe at the Planck temperature was, in a sense, in its most natural, most fundamental state. This perspective shift is important. We tend to think of the Planck temperature as an extreme and impossible condition. And it is. We can never create it in a laboratory. We can never observe it directly. But from the universe's perspective, the Planck temperature is not extreme at all. It's a temperature the universe has already been through, back at the moment of its creation. The current universe, at 2.7 Kelvin, is in an extreme state from the perspective of the early universe. We live in a cold, orderly cosmos that has emerged from a state of unimaginable heat and disorder. This inversion of perspective is worth sitting with. We think of hot as extreme and cold as normal. But in the cosmic timeline, the early universe was normal and hot, while our current universe is abnormally cold. All the structure we see, galaxies, stars, planets, life itself, has emerged from that ancestral heat only because the universe has cooled. We are creatures of extreme cold, living in a universe that has been gradually relaxing away from its initial state of ultimate heat. There's also something poignant in contemplating the Planck temperature in connection with time. The Planck time is the shortest meaningful interval of time, roughly 10 to the minus 44 seconds. At the moment of the Big Bang, when the universe was at the Planck temperature, time itself was likely quantized into Planck time intervals. The universe at that moment was in a state of quantum flux, with time itself uncertain and fluctuating. As the universe expanded and cooled, time became smooth and continuous, or at least it appears to be smooth and continuous, at scales much larger than the Planck time. But that smoothness emerged from an underlying graininess at the smallest scales. Now let's consider the implications of all this for how we think about causality and the explanation. In our ordinary experience, we expect things to have causes. Every event seems to flow from prior events. We ask why and expect to find an answer in terms of prior causes. But at the moment of the Big Bang, when the universe first emerged from the Planck scale regime, this familiar causality might break down. There might be no before to explain the Big Bang, no prior cause to account for it. The universe might simply exist as a timeless, self-contained whole, with its beginning being part of its very structure rather than something that required external causation. This challenges our deepest intuitions about explanation and understanding. We want to know where the universe came from. We want to trace causality back to some ultimate beginning, some first cause. But physics increasingly suggests that this desire might be based on a misunderstanding. The universe might not have a cause in the ordinary sense. It might simply exist. This is uncomfortable for our minds to accept. We crave explanation, and the absence of explanation feels like an absence of understanding. But perhaps true understanding involves accepting that some things, the existence of the universe, the laws of physics themselves, might simply be givens rather than things that require explanation. This brings us to a question that hovers over all of modern cosmology and physics. Why is there something rather than nothing? This is perhaps the deepest question we can ask. The Planck temperature and all the physics we've discussed bear on this question, though they don't fully answer it. We can explain how the universe evolved from a hot initial state to its current cold state. We can explain how stars and galaxies formed. We can explain life's emergence. But the fundamental question, why does the universe exist at all, remains beyond the reach of physics as currently understood. Some physicists and philosophers have speculated that this question might be meaningless, that it rests on assumptions that don't hold at the deepest level. Others believe that someday a complete theory of quantum gravity might provide an answer, that the universe might emerge as an inevitable consequence of quantum mechanical principles. Still others think the question will never be answered by science, that it points toward a domain of inquiry, theology, metaphysics, beyond the scope of empirical investigation. Yet regardless of how we answer these ultimate questions, one thing is clear: the universe we inhabit is profoundly comprehensible to human minds. This in itself is remarkable. Our brains, products of biological evolution on a small planet, have proven capable of understanding the deepest structures of the cosmos. We can think about quantum mechanics and gravity. We can calculate the Planck temperature. We can trace the universe's history back to a fraction of a second after its birth. This capacity for understanding, this ability of mind to grasp the nature of reality, is one of the universe's most extraordinary features. There's a paradox here worth contemplating. We're made of atoms that were forged in stars. The atoms in your body came from supernovae billions of years ago. You and I are made of stardust, literally. And this stardust has organized itself into beings capable of thinking about stars, about the universe, about the very processes that created us. The universe has become conscious of itself through us. We are the universe knowing itself, contemplating its own origin and nature. This is a fact worth sitting with, worth allowing to sink in fully. Let's pause for a moment. We've wandered through philosophical territory, reflecting on the wonder and mystery of existence. We've thought about limits and infinities, about causality and explanation, about the remarkable fact that we can understand anything at all. These reflections are just as important as the technical discussions we engaged in earlier. Science and philosophy are not separate domains, but deeply intertwined. The Planck temperature is simultaneously a technical concept in physics and a symbol of the frontiers of human understanding and the mysteries that lie beyond. As we prepare to move toward the closing sections of our journey, let's carry with us this sense of wonder. Wonder at the complexity and order we've discovered. Wonder at the limits we've encountered. Wonder at the fact that questions remain unanswered. Wonder at the beauty of a universe that is both comprehensible and mysterious, both ordered and uncertain. This wonder, this sense of awe at existence itself, is perhaps the most important gift that contemplating the Planck temperature and the deep physics of the universe can offer us. The Planck temperature is not just a fascinating scientific concept, it's an invitation to contemplate the profound nature of reality, to acknowledge both what we know and what we don't know, and to approach the universe with humility, curiosity, and appreciation for the extraordinary privilege of being conscious. Beings capable of understanding even a small fraction of the cosmos's deep structure. Now, as we near the final stretch of our journey, let's gently gather together all the threads we've woven throughout this exploration. We've covered so much ground, from the basics of heat and temperature to the extreme physics at the Planck scale. Let's see how it all fits together, how each piece we've explored connects to form a coherent whole. This is where we find harmony in complexity, where disparate ideas resolve into elegant unity. Think back to where we began. We started with something simple. Heat is motion. Temperature measures the average kinetic energy of particles jiggling and vibrating. It seemed straightforward enough. But as we've journeyed deeper, we've discovered that temperature connects to nearly everything in physics. It connects to quantum mechanics through the quantization of energy. It connects to gravity through Hawking, radiation and black holes, It connects to thermodynamics and entropy. It connects to cosmology through the early universe's cooling history. Temperature, it turns out, is not just a simple measure of thermal motion. It's a thread that runs through the entire fabric of physics, connecting domains that at first seemed unrelated. Consider the journey the universe has taken. It began at the Planck temperature, in a state of quantum gravity where our current theories cannot reliably describe what was happening. As it expanded, it cooled. Each drop in temperature unlocked new physics, new possibilities. At the gut temperature, the temperature of about 10 to the 27 Kelvin, where we think the grand unified theories operated, the strong nuclear force, the weak nuclear force, and electromagnetism were unified into a single force. As the universe cooled below this temperature, these forces separated and became distinct. At roughly 1 trillion Kelvin, nucleons, protons, and neutrons could form. At 1 billion Kelvin, nuclei could fuse to create the first light elements. At 3000 Kelvin, atoms could form. At still lower temperatures, neutral atoms could cluster under gravity to form galaxies and stars. And at the relatively cool temperatures inside stellar cores, millions of Kelvin, complex nuclei could form through fusion. Finally, at the frigid temperatures of planetary surfaces, hundreds of Kelvin, chemistry became possible, and eventually, life. Each temperature threshold represents a phase transition, a point where the universe shifted from one state to another, unlocking new phenomena. This is deeply reminiscent of how matter undergoes phase transitions on Earth. Water freezes into ice at 273 Kelvin. It boils into steam at 373 Kelvin. But the phase transitions in the early universe were far more dramatic. They weren't just changes in the state of matter, but changes in which forces and particles existed and how they interacted. Now, notice something elegant about this progression. It moves from simplicity to complexity. The very early universe, hot and dense, was simpler in a certain sense. Fewer distinct structures, fewer types of particles and forces visible. But as the universe cooled and expanded, complexity emerged. Stars formed. Elements heavier than iron were created. Planets emerged. Chemistry became possible. Life arose. The universe moved from a state of simple, undifferentiated heat to a cosmos of staggering complexity and richness. But here's a paradox. According to the second law of thermodynamics, entropy, disorder, always increases. The universe should be moving toward greater disorder, not greater order. How can complexity arise in a universe moving toward maximum disorder? The resolution is subtle but important. The universe as a whole is indeed moving toward maximum entropy. But locally, in certain regions, entropy can decrease as long as it increases even more somewhere else. Life and complexity are possible because they're supported by an enormous increase in disorder elsewhere, the radiation spreading out into the vast empty spaces of the expanding universe, the order of the Big Bang being gradually converted into the diffuse heat of empty space. In this way, every structure in the universe, every galaxy, every star, every planet, every organism, is a temporary eddy of order in an ocean of increasing disorder. We are not violating the second law by existing. We are enabled by it. Our existence is a consequence of the universe's tendency toward disorder. The Planck temperature, with its state of absolute order and concentration, naturally gives rise to the complexities we observe through the process of universal cooling and expansion. Let's think about how different scientific domains illuminate this progression. Quantum mechanics explains how particles behave at different energy scales. General relativity explains how gravity shapes space and time. Thermodynamics explains how energy is distributed and how order becomes disorder. Particle physics explains what happens at extreme energies and temperatures. Cosmology synthesizes all of these into a unified narrative of cosmic evolution. And each domain, examined carefully, points toward physics at the Planck scale as a fundamental frontier. The Planck temperature also plays a subtle but crucial role in connecting these domains. It's the temperature at which quantum effects and gravitational effects become equally important. It's the temperature scale naturally defined by combining quantum mechanics, through Planck's constant, and gravity, through the gravitational constant, with relativity, through the speed of light. This natural emergence of the Planck scale from the fundamental constants is not coincidental. It reflects a deep truth about how nature is structured. The Planck scale is where the fundamental scales of physics intersect. In a sense, everything we observe, the entire universe with all its structure and complexity, is a consequence of the transition from a state at or above the Planck temperature to a state vastly colder. We live in the cooling residue of an infinitely hot beginning. The history of the universe is the history of progressive cooling, progressive ordering, progressive emergence of complexity. And this entire history is enabled by the existence of the Planck temperature as a frontier, a boundary beyond which our current understanding cannot extend, but where new physics awaits discovery. Let's also think about what the Planck temperature tells us about the nature of physics itself. The fact that a maximum temperature exists suggests that temperature and energy are not infinitely divisible at the quantum level. This connects to the deep principle of quantization that runs through modern physics. Just as energy comes in quanta, just as electric charge comes in quanta, perhaps temperature and spacetime itself come in quanta at the deepest level. The Planck scale represents the scale at which this quantization becomes crucial, where quantum effects become dominant. This unification of insight, the realization that quantization applies not just to energy and charge, but to space and time themselves, is one of the deepest principles suggested by modern theoretical physics. If true, it would represent a profound reorganization of how we understand reality. Reality would not be fundamentally continuous, but fundamentally discrete. Spacetime would not be a smooth manifold, but a discrete structure, perhaps woven from tiny loops or strings or some other quantum substrate we haven't yet imagined. Now, let's consider how this all relates to the questions we began with. We asked, does the universe hit a maximum heat? And the answer is yes, both in a practical sense and in a fundamental sense. Practically, the Planck temperature represents the highest temperature that anything can have. Beyond that point, the concepts of temperature and heat break down. Fundamentally, the Planck temperature represents the boundary of our current understanding, the frontier where quantum gravity effects become dominant and new physics must emerge. We also asked, what happens when the universe approaches this maximum temperature? And we've learned that it becomes difficult or impossible to describe using our current physics. Space and time become uncertain. Particles and fields intermingle. Causality might break down. We encounter paradoxes and infinities in our equations. This is not a failure of physics, but a feature. It's a message that we've reached the boundary of a domain and need new tools to proceed further. And finally, we asked, what did the universe look like during its first moments, when everything existed near this limit? We've learned that the answer likely involves quantum gravity, that it probably transcends our current understanding, and that it might involve physics so different from our everyday experience that we can barely conceive of it. The first Planck time of the universe remains shrouded in mystery, a frontier we've glimpsed but not yet crossed. But notice something important. Despite this mystery, we're not helpless. We can trace the universe's history backward with confidence to a fraction of a second after the Big Bang. We can observe the cosmic microwave background and learn about conditions millions of years after creation. We can study the properties of black holes and probe the connection between thermodynamics and gravity. We can develop theoretical frameworks and test them against observations. We're making progress toward understanding, even as we acknowledge the limits of that understanding. This balance between progress and mystery, between confidence and humility, is characteristic of good science. We know enough to be impressed by what we've learned. We know enough to ask increasingly sophisticated questions. But we remain aware that profound mysteries remain, that the universe is stranger and more wonderful than we've imagined. This is the spirit in which we should approach the Planck temperature, with appreciation for what we understand, with curiosity about what we don't, and with humility about the limits of human understanding. Let's pause and reflect on the journey we've taken together. We've started with heat and temperature, passed through quantum mechanics and gravity, explored black holes and the early universe, examined theoretical physics at its frontier, and contemplated the philosophical implications of all this knowledge. We've woven together threads from different domains of science into a tapestry depicting the universe's nature and history. We've seen how temperature, in its various manifestations, connects the smallest scales of reality to the largest, the earliest moments of cosmic time to the present, the known to the unknown. The Planck temperature stands at the center of this tapestry. It's a point of convergence where quantum mechanics, gravity, and thermodynamics meet. It's a frontier where current physics breaks down and new physics must emerge. It's a symbol of human curiosity and the limits of human understanding. It's a reminder that the universe is vast, ancient, and strange beyond our ordinary comprehension. And it's an invitation to keep exploring, keep questioning, keep wondering about the nature of reality. As we move now toward the closing sections of our journey, carrying all these insights and reflections with us, let's allow ourselves to feel the weight of what we've learned. Let's sit with the wonder of it. Let's acknowledge both the tremendous achievements of human understanding and the profound mysteries that remain. And let's prepare ourselves to drift gently into sleep, carrying with us the memory of this voyage to the Planck temperature and back, a journey that has brought us to the very edge of what we know and what we might yet discover. Does the universe hit a maximum heat? It's the question that brought us here, whispered softly at the beginning, like a curious child asking if the stars ever get tired of shining. And after wandering gently through temperature and thermodynamics, through quantum mechanics and gravity, through the early universe's cooling journey, and the mysteries of the Planck scale, we find ourselves circling back to that question, still wondering, still marveling at the beauty of the answer. Yes, the universe does hit a maximum heat. That maximum is the Planck temperature, roughly 10 to the 32 Kelvin, a number so large that it almost stops feeling real, yet one that emerges naturally from the fundamental constants that govern our universe. This isn't an arbitrary limit. It's not something we invented or imposed. It emerges from the very structure of physics itself, from the way quantum mechanics and gravity weave together at the smallest scales. At the Planck temperature, space and time become uncertain. Gravity becomes as strong as the other forces. The concepts we use to describe heat and temperature begin to lose their meaning. This is the frontier, the boundary beyond which our current understanding cannot extend. We've learned that temperature is far more than a simple measure of how fast particles are jiggling. It's a thread connecting the smallest scales of reality to the largest. It's intimately linked to time itself, to entropy, to the very structure of space. We've seen how the universe began at the Planck temperature, or at least began in a state that rapidly cooled from such extremes, and has been gradually cooling ever since. Each temperature threshold the universe passed through unlocked new physics, new structures, new possibilities. From the unimaginable heat of the first Planck time to the relative coolness of today, the universe's history is a story written in temperature. We've explored how quantum mechanics transforms at extreme temperatures. We've examined the profound connection between black holes and heat, discovering that smaller black holes are hotter, that the tiniest black holes would have temperatures near the Planck temperature. We've traced the universe's cooling journey from the first microseconds after the Big Bang through the formation of atoms, stars, galaxies, and ultimately, life. We've seen how observations from NASA, ESA, and telescopes like JWST have provided empirical confirmation of theoretical predictions about the early universe. And we've contemplated the mysteries that remain: quantum gravity, the nature of time itself, the ultimate origin of existence. We've discovered that the Planck temperature represents more than just a physical limit. It's a symbol of the frontiers of human understanding. It marks the boundary where our current theories break down and new physics must emerge. It reminds us that for all we've learned about the universe, profound mysteries remain. Scientists continue to develop new theories, string theory, loop quantum gravity, and others, attempting to understand what happens at the Planck scale. These theories are elegant and sophisticated, yet none has been definitively proven. The truth about quantum gravity still awaits discovery. Maybe the Planck temperature doesn't represent the end of physics. Maybe it's just the end of our current understanding. Maybe there's deeper physics beyond it, physics we haven't yet imagined. Maybe space and time are not fundamental but emergent phenomena arising from something more basic. Maybe information is more fundamental than matter and energy. Maybe consciousness plays a role in understanding reality that we haven't yet recognized. Or maybe the Planck temperature truly is a fundamental limit, a boundary beyond which nothing can go. The universe itself doesn't tell us which is true. It simply presents us with the mystery and invites us to solve it. Maybe that's the whole point. Maybe the beauty of physics lies not in having all the answers, but in the ongoing process of questioning, discovering, and contemplating. Maybe the Planck temperature is beautiful precisely because it marks the edge of knowledge, the frontier where wonder and mystery reign. Every answer we find opens new questions. Every frontier we cross reveals new frontiers beyond. This perpetual mystery, this endless horizon of understanding, gives science its meaning and power. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interested in sharing these ideas with you. Though, if I was, well, at least you've learned quite a lot about the Planck temperature, about extreme heat, and about the very foundations of physics. And if you're already drifting off towards sleep, may your dreams be filled with gently cooling universes, with quantum particles dancing at Planck scales, with the soft whisper of ancient light traveling across billions of years to reach your ears. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share with us. Are you perhaps a physicist pondering these mysteries in a quiet office late at night? Or simply someone who finds the deep structure of the universe strangely comforting? Are you in a cozy bed in London at 2 a.m? Or relaxing in a comfortable chair in Sydney as morning light filters through your windows? Are you a student seeking to understand the Planck temperature for a class, or just a curious mind wandering through the cosmos before sleep? Each perspective is valuable. Each brings something unique to this community we're building together. If you found this gentle journey into the Planck temperature, into quantum gravity, and into the extreme physics of the early universe relaxing or informative or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture, but it helps me keep bringing you more calming, curious content from the world of science and beyond. Whether you're here to unwind before sleep, to expand your understanding, or simply to spend time with ideas that fascinate you, your support means everything. It tells me that this channel is touching lives, that these quiet explorations matter to people, and that there's value in approaching science with gentleness, wonder, and an appreciation for mystery. Thank you for joining me on this journey through the Planck temperature, through quantum mechanics and gravity, through the early universe and the frontiers of physics. Thank you for sitting with me as we contemplated the extreme heat of creation, the cooling of the cosmos, and the limits of human understanding. Thank you for bringing your curiosity and your open mind to these profound questions about the nature of reality. This journey we've taken together, from temperature to Planck scales, from observations to theory, from what we know to what remains mysterious, is one of the greatest privileges of my life to share with you. Sleep well, dream deep, and may your mind rest in the peaceful knowledge that we live in a universe governed by elegant principles, a universe that has existed for billions of years and will continue for billions more. May you dream of cosmic scales and quantum mysteries, of stars being born and galaxies forming, of the infinite complexity emerging from the simplicity of fundamental physics. And may you carry with you, when you wake, the sense of wonder this journey has kindled, the recognition that you are made of stardust, that your atoms were forged in stellar furnaces billions of years ago, that you are part of this vast, ancient, beautiful universe. Remember, somewhere in the quantum foam at Planck scales, infinite variations of you are contemplating these same mysteries, existing in superpositions of sleep and wakefulness, dreaming and thinking. The universe is stranger and more wonderful than we can imagine, and we are privileged to be conscious beings capable of contemplating even a small fraction of its mysteries. Good night.